So we are going to continue from rank and nullity. We are going to have our extend this understanding of linear transformation for in terms of tensor products of transformations. So we had previously had some idea of tensor products and how two finite dimensional vector spaces, what were the rules or the algebra of those tensor products. So this time we are going to have see some properties of these, how we study them as part of that matrix transformations. So before we are going to study in that sense, we are going to have some tensor products of transformations. So one has to remember the product is a product of those vector spaces in consideration, finite dimensional vector spaces whose products, for example, which are deemed as tensor products. So let U and V be finite dimensional vector spaces, finite dimensional vector spaces or same fields, and let A and B be any two linear transformations, any two linear transformations on U and V respectively. So now the point is, so we can define the linear transformation C on a vector space. We define a linear transformation C on a vector space of all bilinear forms of all. So previously when we had bilinear forms, so one is the linear transformation, another is the bilinear transformation. The algebra got a bit more complicated, and we had a specific way of bracket way of how to see how bilinear transformations transform. So in the same sense, so if two linear transformations are respectively on vector space W of all bilinear, so it is not one transformation. Bilinear, not here. It's not bilinear transformation. Bilinear forms. It's a word here. So U cross, we can write it as C of X of Y can be written as this AX and BY. They are the scalars associated with this. And the tensor product C can be written in terms of tensor product can be written in terms of A cross B. And the transformation across C can be naturally C of Z of this is equal to Z of C of this, where Z is in U cross V and omega is in W. And Z goes like and Z of this is so we have translate them in terms of A and B, so it will be equivalent to, so just you can have this C outside. So C of Z naught, this can be written as Z naught C of omega, and here Z is written in terms of X and Y. So it will be X naught cross of Y naught C of omega. Now in the simplest cases, if we will further see it, we can write it like, we can get a C, we can get it here in the prefix, which should not matter, it should not matter. So X naught, Y naught, and further omega can be kept, and this can be written in terms of A and B. So it's X naught. Or from this, you can infer that C of Z naught is going to be cross. Now we can, so this is in binomial forms. We can, if C is tensor product of A and B, and we can the A and B can also be written in terms of elements X naught and Y naught. So we can write it in terms of like this. Now there are, the way we have enumerated properties right across. What are the property vector species? In whichever way, 1, 2, 3. So in the same way, we are going to enumerate some formal rules from which those properties can be just understood or derived. So rules are, for example, rule number 1 is this. This is rule number 1, and second is, so there are, some of them are very simple rules, you need not to, so it's simple. So if it's a unitary element, tensor products of two unitary elements will give a unitary element. Tensor product of this with a 0, it should give 0 only. And if there are two elements, if there are A1 plus A2, if you have an associative scalar addition, so you can write this property should hold for these tensor products. In the same manner, if A cross then it will be equivalent to A cross B2. So in a similar manner, we can have, we multiply it by scalar alpha A into alpha B. So A and B are this. It's the scalar multiplication of two tensor products. Then you should have scalars outside these tensor products between these two spaces, just fine. Now this property 7 and 8 become more slightly, they are a bit slightly, in the sense they can, these properties can be straight away, you can, this one line, you can just see it. The property 7 and 8 have a bit of thing, we said that the inverse of elements, two elements is the individual inverse of the product of elements. So here the product is of the tensor products, inverse of tensor products of two elements. It should be whether it is inverse of A cross B inverse, whether it's A inverse tensor product of B inverse. And the eighth property is A1, A2. It's tensor product of this and B1, B2. So we can have first you do tensor product of this with this, then A2 with B2. So if others are straightforward, so they may be a bit trickier, and there should be a way we can just have, for example, we can somehow see how we can prove them, or we can have a proof means we can have a way to justify them, how we can justify the existence of these statements in some from prior principles. So if we just take the arguments of the book, formula 8 follows from the characterization of the tensor products from the following computation. So A1, A2, cross, so the justification of this is from this computation. A1, A1 cross, B1, B2 is X cross Y. So you can write it as A1, A2 X cross B1, B2 Y. So we can write it like this: A1, A2 cross B1, B2 cross of X1. So we can write it. So for A1, A2 cross. So we have done A1, A2 cross of X. Then B1, B2 cross of Y. Should be this. So we have A1, A2 cross X and A1, B2 cross Y. First we did this tensor product, then we did this. So or further, we can further write it as A1 cross of B1, A2 cross of B2, and X cross Y. Or, so that's the later thing. So first we'll do step by step. So A1 cross of B1. Now A2X cross of B2Y. Now again we are going to the final step. A1 cross B1. So A2 cross B2 tensor product and X cross Y. So this is the thing. So as an immediate consequence of this. So as an immediate consequence of 9, from this we can follow. So A cross B is equal to A cross, tensor product A is 1 cross B, or from this you can have A1 cross B into, so it's sort of commutativity is there. The commutativity exists, and these product of these tensor products. And to prove this seventh, this one, what we are going to do is that if A and B are invertible, and from A cross B and A inverse and B inverse, so it follows that if A and B are invertible and 7 holds, 7 means this holds, so conversely Suppose A cross B is invertible. So we'll just so we are going to use the arguments of adjointness and invertibility. A B is 0. So this means B is equal to or if AB is equal to 1, this means B is A inverse. So we are going to use the argument of invertibility to show it this way. For example, we are going to show it in the sense that we are going to show it in the sense that we define tensor products for finite dimensional space only, and we may invoke that theorem too. So, for example, Ax is 0 implies that x is 0, and By is 0 implies y is 0. And from this, and Ax tensor product of By is A cross of B, first A with B, then X with Y. Is X cross of Y. This is equal to 0. So either from this, if it's 0, either X is 0 or Y is 0. So since B is 0 is impossible, we may find that vector By is not equal to 0. So why? Since B is equal to 0 is impossible. Why? We may find that the vector Y, so that the By is not equal to 0. So just wait for some second. Why would say that B should not be equal to 0 or B is equal to 0? So what the argumentation is like this. The argumentation to this is that so from this, that if A and B are interchange, this means B is invertible. So invertible means B is equal to B inverse. So B and B inverse are there. So this means what? This means what? So the argument is just give me some time. And suppose that in so the argument is the same, that if A is 0, this is 0, then B is 0, then from this B can be shown to be invertible. So either X is 0 or either Y is 0. From this you can show that if this tensor product of these two elements, the inverse of tensor product is equivalent to the individual tensor products of elements A and B from this argumentation. And from this argumentation, we should show that B is also invertible. So another the interesting part of this as a side story is for example, we use sometimes invoke chronicle delta. We also represent tensor products as Kronecker product of matrices. He might have previously also known the properties of matrices in terms of not matrices, the properties that, of a delta function. Chronicle delta j, where I is equal to j or I is not equal to j. In the later case it's 1, in the later case it's 0. So how how elements I and j, so these I and j can be two components. So how we translate them in the language of matrices? If we use rows and columns, and i's and j's are rows and columns, and if we represent these tensor products in terms of matrices, how these components of the components will be represented as chronicle product of matrices. For example, if chi is equal to x1, so on and xn, y is xn is equal to this y1 and ym, b bases in U and V. There are two vector spaces which are having bases U and V, and let A is A of this and B is B of Y. Y. So you can represent this one as, so first we'll write this. So we can represent this as alpha ij in terms of matrices. Alpha ij, I and j are rows and columns. In the same way, B is B of y is equal to beta ij. It's also, so he has used word PQ. So we are following the book. So it's PQ. So if it's alpha ij, so these are rows and columns. Now what's the tensor product of A cross of B? So we are going to see product of these alpha ij and beta pq. X A cross B in the coordinates x cross I cross y of p. So, but it has become slightly more complicated. So we have to arrange them in terms of, for example, we have to arrange them in terms of x1 cross y1, x1 cross y2, so on, and x1 cross ym. The same way x2 cross y1, x2 cross y2, so on, and x2 cross ym. And you can have other way also, y1 cross x1, y1 cross x2, y1 cross xn, y2 cross x1. So in the reverse direction. So in the sense that the tensor products of A cross B can be written as, in terms of elements, xj cross of y of j is equivalent to, now here, so it's axj cross byq. Now we are going to write this A and B in terms of A in terms of alpha ij, A in terms of alpha ij, and B in terms of bpq. So we can write it like this. It's product of matrices basically. This is one. So it's from I. This is P. And this is beta PQ and YP. So you can have these scale, you can just have them in the brackets. So you can represent it as I, sigma I and sigma P, alpha ij, beta PQ. So it's IXI cross YP. That's it. So that's it. That's the way we have written in terms of transformations. We just so it's a representation. How can I write a tensor product of individual elements in terms of these alpha IJs? Where alpha IJs are rows and columns. Now, if we want to see how they will span it in terms of pairs. Now there is not one pair, there are two pairs, IJ and PQ. So it was simple row and column, so it would have been simple. Now, but it's row, column, and the indices are not, you cannot reduce them somehow, I, J, P, Q. Or you can reduce them, but it depends upon how you take the values of I, J and P, Q. If they are repeated indices, if J is P, then you can just reduce the number of this thing. Otherwise, in the general sense, we can write it, the matrix can be written in the form, for example, for the pairs, see I, P and JQ can be written as alpha IP, RG, beta PQ can be written as alpha 11, beta 11. So it's a tensor product, alpha 11, beta 11, alpha 1. So we will write it here. So it will be alpha 11, beta 11, alpha 1, beta 1, and so on and so forth. Then alpha 1n, beta 1n, alpha 1n, beta 1m. Sorry, alpha 1n, beta 11, alpha 1n, beta 1m. So you can see this is alpha 11, beta m1. So it's 1m, it's m1. So it's alpha 11, beta 1, alpha 22, beta 22. So in the same way, alpha 33, the same way, alpha 11, beta mm, beta m1, so in the same way. So you can have alpha nn, beta 1, alpha nn, beta. So the last one will be alpha nn, beta mm. The other elements you can see it, alpha n1, beta 1n. So if it's n1n, it will be n1. If it's 1m, it will be, if it's 1m, it will be n1. It's 1m, it will be n1. It's m1. So you can accordingly see things going on. It's alpha n1, beta mm, alpha nn, beta m1, alpha nn, beta 1, alpha nn, beta mm, so on and so forth. So you can see the indices accordingly. The point to mention is only to show that if you increase it, if you 1 1 1 1, so it will be nn, but it will be 1 1 mm, and these are this. If it's 1 1, it's n1, it's 1 n. So you can see accordingly how these alpha ig and beta pq, they are two indices, how they will be seen as a part of this matrices. You can write it as a matrix A cross B, where A and B are having these elements. These rows and columns, you can see it like this. And if you want to write it in terms of a more condensed notation, so it will be So alpha 1, 1, beta 1. So we can have this this free indices of this here. It's beta. Alpha 1, 1, alpha 1, 1, alpha 1. So it will be same. So it will be alpha 1, 1. So you can put it like this. Alpha 1 and beta. The last one will be alpha n1. Alpha n1. B and so on and alpha n. And this matrix is known as Kronecker product of A and B in that order. Yes. So the rule is easy. The rule is replace each element. What's the rule? Rule is replace each element alpha ij by n cross n elements of A, this matrix A, and beta alpha j and m cross m. The other one will be this is n cross n. It will be m cross m. Sorry, this is n cross n. This is n cross m of this element beta. If it's also alpha ig, here it was pq, but you don't want to change alpha ig. You just say these are rows and columns. So in one case it's n cross n, in another is n cross n. The other thing is maybe let it be as a part of an exercise. Further, the point is how we can represent them. This entire we have written it in terms of matrices. But the next section, if you are going to read, is that we can also represent them in terms of some part of as determinants. So matrices and determinants have there is some difference. So you can write these vector spaces or tensor products also in terms of determinants in that multilinear algebra. And that representation is not, you can just have it, how we can represent the elements of them in terms of determinants, and there are some properties of those determinants we are going to see in the next class. So in today's class we just try to see how we can represent these tensor products in terms of these matrices, and how those in terms of ultimately these as a Kronecker product of two matrices A and B, where these are the individual elements and these are the indices which take different values I, J and beta, which are in turn part of those tensor product of two elements into consideration. So in the next we are going to use the same thing. Here it was for tensor product for elements in matrices. We can use also in the theory of determinants, proper values, and how we can solve the way we solve equations in the determinant form, how we solve them, how we take eigenvalue problems and other problems in mathematics and general also. Stop.